Okay, so today's notes are our last section for Unit 5. It's on theorems about roots of polynomials. It's section 5.5, and our content objective is to solve equations using the rational root theorem and the conjugate root theorem. And our language objective is to use the correct terminology to explain and describe these theorems. So we're going to start off with the rational root theorem, which I've started writing out here on the page. So it starts by saying let p of x equal a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 0 be a polynomial with integer coefficients. I put a reminder here, integers are just plus or minus whole numbers. So before we actually delve into this, I'm sure many of you were a little intimidated by that expression. That's just saying whatever the degree of the polynomial is in descending order. So basically, let your function be a polynomial in standard form, and the coefficients need to be integers or positive or negative whole numbers. So assuming we're working with a polynomial in standard form with positive or negative whole numbers as coefficients or integer coefficients, what the rational root theorem tells us, so what this theorem tells us is that there are a limited number of possible roots. So there are a limited number of possible roots, and we know that integer, which again are our positive or negative whole numbers, so integer roots or x-intercepts must be factors of a sub 0, which is just our constant. So if you notice here, a sub 0, that's just the constant of our polynomial, or the term without a variable. So if we have integer roots or positive or negative whole number roots of a polynomial, then those integer roots must be factors of our constant. So that's what this is saying if we're breaking it down. And then we also know that rational roots, so just as a refresher, rational roots are numbers that can be written as fractions. So numbers that can be written as fractions are rational. So rational roots must have a reduced form of p over q, where p is a factor of a, the constant, or a sub 0, sorry, the constant, and q is a factor of a sub n, which is just the leading coefficient. So what this is saying is, to sort of break this down again, because I know there's a lot of jargon in here. So this is saying our rational roots, or numbers that can be written as fractions that are x-intercepts or solutions to a polynomial, must have a reduced form of p over q, where p is a factor of the constant and q is a factor of the leading coefficient. This means that we can make a list of possible roots for a polynomial in order to solve it. So it limits from infinite possibilities of roots into a finite number of possible roots for our polynomial, which is a big deal. So we're going to do an example just to show how this can work, and then we'll do another example to actually use it to solve. So I want to first examine what are the possible rational roots of 2x cubed minus x squared plus 2x plus 5 equals 0. So again, just as a reminder, our only possible rational roots, which I'm abbreviating RR, are p over q. So we're going to start by determining our p-values, or determine possible p-values. So p, again, if we look back here, p is the factors of the constant. So our constant here is 5. So I need to find factors of 5, which are pretty easy. 5 is prime, so I just have plus or minus 1 or plus or minus 5. Those are my only two factors of 5, so those are my only possibilities for my p-value. So then we're going to do the same thing for q. So the possible q values, q is our leading coefficient. So we're looking at 2, this was for 5, q is for 2, our leading coefficient. So again, 2 is prime, so I just have plus or minus 1 and plus or minus 2. So I've determined my possible p-values, my possible q-values, because they, again, are just going to be factors of our constant over factors of our leading coefficient. So now I'm going to write all the possible values of p over q. So these are going to be, this is going to be the list of all the possible roots of this polynomial. So p over q could equal, I'm going to just go like this. So start with my first number and go over each one. So I'm going to have plus or minus 1, because 1 over 1 would just be plus or minus 1. And then plus or minus 1/2. And then I do the same thing with 5. So I have plus or minus 5 over 1, and then plus or minus 5 over 2. So again, I just did 1 over 1, 1 over 2, 5 over 1, 5 over 2, and that gave me my entire list. But again, they could be positive or negative, so I put plus or minus. So these are all the possible rational roots. So that's all we have to do for that. You just make a list of all the factors of your constant over all the factors of your leading coefficient. All right, so I know hopefully you understand how the rational theorem works or what it's saying at this point, but why are we learning it? What will this actually help us do? I'm going to go move on to an example of that next. So I'm going to flip the page for that. While I'm doing that, if you can just send me a quick email to let me know you're listening. This is a critical lesson to listen to, so I want to make sure you're all hearing it. So please make sure you send me a quick email and let me know that you actually took the time to listen to this and understand what I'm talking about. So for this example, I'm asking you, what are the rational roots of 15x cubed minus 32x plus 3x plus 2 equals 0. And so this is not just asking us to list the possible rational roots, it's actually asking us to solve it. So to do this, we're going to start it with the same process we just did. So I'm going to determine possible p and q values. So again, for p, I'm just looking at my constant, so I have plus or minus 1 or plus or minus 2 because 2 is prime. And for q, I'm looking at my leading coefficient, which gets a little bit different this time. So I know there's 1 and 15. So I'm going to keep them in order. So I'm going to do 15 over here. And then I know 3 and 5. 2 doesn't work, 4 doesn't work, 6 doesn't work, and 7 doesn't work. 8 doesn't work, 9 doesn't work, 10 doesn't work. So we have 1, 3, 5, and 15 as my possible q values. So I've determined my p and q values. So now I need to make my list of all possible rational roots. So this is going to be all the p over q values. So this is all p over q. So I'm going to go in order again. So I'm going to do plus or minus 1 over 1, plus or minus 2 over 1. Then I have plus or minus 1/3, plus or minus 1/5, plus or minus 1/15. Sorry, I got carried away with the ones. I should have done the 2's in between. And then I also have plus or minus 2 over 3, plus or minus 2 over 5, and plus or minus 2 over 15. So as long as you got all 8 possible roots, so you have 1 over 1, 2 over 1, you did all the possible combinations, these are all your possible rational roots. So we have our list of our possibilities. Now we need to narrow it down and find one that works so that we can continue on. So all I have to do, since it's only cubic, I have to find one that works at this point to move on. So to do that, I'm going to test possible roots. until there is one that works. So this, in theory, could take a little while, but I would recommend start with whole numbers because they're easier to calculate. So let's start with our whole numbers. So first one I'm going to plug in is, we'll call it f of 1. If I plug in 1 here to my original equation, I get 15 times 1 cubed minus 32 times 1 plus 3 times 1 plus 2. And then I have to evaluate that. So luckily this is just 1. So 15 minus, oh sorry, this was squared also. 15 minus 32 is negative 17, plus 3 is negative 14, plus 2 is negative 12. So that one does not work. So then I'm going to try negative 1. So when I do that, I get negative 15 minus 32 is negative 47, minus 3 is negative 50, plus 2 is going to be negative 48. So that one does not work either. So I'm going to try 2 next. So I'm just going through my list, starting with my whole numbers because those are easier to evaluate. And I plug in 15 times 2 cubed minus 32 times 2 squared plus 3 times 2 plus 2 equals, and this gives me 8 times 15 is 120. 2 squared is 4 times negative 32 is negative 128. So I have 120 minus 128 is negative 8. Plus 6 is negative 2. Plus 2 is 0. So this one, when I evaluate it out, gives me 0. That means that 2 is a root of that polynomial. So I found one of my x-intercepts by using my list. So now what's useful about this, the reason we're learning this process, is now that I've used this list to narrow down, find one possible root through sort of checking or process of elimination, I now can continue and factor this. So I'm going to, for step 4, use synthetic division. So I'm going to divide by this root 2. So I have 2 here, and I'm going to divide this polynomial by the known root that I have. So I write all the coefficients of this down, draw my line, carry down my first term of 15. 15 times 2 is 30. I get negative 2. Negative 2 times negative 2 is negative 4. 3 plus negative 4 is negative 1. Negative 2, 0. So again, no remainder. That means I did this all correctly. So I use synthetic division divided by my known root, and now I can write my new equation. To write my factored form. So now I know I have my new polynomial of 15x squared minus 2x minus 1 being multiplied by my root of x minus 2. So now I can factor this even further. So I'm going to use middle term splitting method. So I do 15 times negative 1. So I'm finding factors of negative 15 that add to negative 2, which I know 15x squared is going to be negative 5x plus 3x minus 1. And then I'm going to group them and use middle term splitting method again. So I know I can take a 5x out of here, and I'm left with 3x minus 1. And that already matches that. So I just take a 1 out of there. And so my factored form is 5x plus 1 times 3x minus 1. And then I carry down my other factor that I had there all along. So here what I was doing was fully factor what's left. So I fully factored this all, and now I'm going to use the zero product property to find all my values. So I know 5x plus 1 equals 0, or 3x minus 1 equals 0. And this one I already know, x equals 2 is one of my roots. So then I get x equals negative 1/5 because I subtract 1 and divide by 5. So that's a possible root. And then I get x equals 1/3. And these are my 3 possible roots of this polynomial. So I've fully solved out for this polynomial using the rational root theorem. The last thing I want to mention super quickly, sorry these notes are a little long, I'm going to flip the page, is the conjugate root theorem. And I'm not going to take the time to write the full complicated version of the theorem since these notes are already a little bit long, but all this says is that If a plus root b is a root, then so is a minus root b. And similarly, if a plus bi is a root, then so is a minus bi. So what this means is if you have irrational roots, so in this case, we're assuming b doesn't have a pretty square root. So if you have a solution that's a plus a square root of something, then a minus that square root should also be a solution. So a conjugate is something that's the same but opposite signs in the middle. So if you have irrational roots or imaginary roots that are written like this, then you know that their conjugate is also a root. So one super quick example, if a quartic polynomial has roots square root 2 and 1 plus I, what are the other roots? And so you would just do the inverse or opposite sign. So the other roots would have to be the negative root 2. So again, plus or minus root 2, it makes sense that you have to have the negative version. And 1 minus I, so again, the other version of that root. So these would be our other roots using the conjugate root theorem. We'll practice applying that in class, and we'll talk briefly about the fundamental theorem of algebra, but that's all for now. Make sure you write down any questions, comments, concerns you have so we can go over them together in class.